here this becomes very, 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 very boring. If we combine the first two equations of motion that we derived, we can find an alternative formula for the displacement of the object. How do I mean? Well, if I take equation 4 that we just derived, this equation here, right? Meaning if I say from equation 4, which is this equation here defined by change in x is equals to initial velocity plus final velocity over 2 divided by change in t. Then I substitute equation 1 here. I say substitute equation 1. Now let's go back to equation 1 just to remind ourselves how it looks like. So equation 1 is given by Vf is equals to Vi plus A times change in t. So this means where we see the V final, we can replace it by Vi plus A times change in t. Alright, now let's do that. From this equation that we have here, we will have change in x, because I'm saying from this equation 4 we substitute 1. So we'll have delta x is equals to V initial plus final velocity as per equation 1 would be given by V final plus A times change in t. And all this is still divided by 2, because what I've done, I've just replaced this by this guy here, right? So that I still have here the delta t. Now from here, this becomes very, 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 very boring, because we're just going to simplify this. Now this would mean I'll have my change in x being equal to, notice that I've made a mistake here, because we don't have V final here, we actually have Vi. Remember, we are substituting the Vi, the Vf with Vi plus A times change in t, right, to simplify this. Now this would mean if I say Vi plus Vi, it will give me 2 Vi, and I have here A times change in t, all divided by 2, and I have a change in t there. Now what I'm going to do here is that I'm going to divide this by a 2 and divide this by a 2 as well, so that I have here change in x is equals to 2 Vi over 2 plus, here I'm going to have a change in t over 2, but remember I still have the change in t outside there. Notice that the 2 and the 2 would cancel, and here I'm going to have more like 1 over 2, right? And what I'm going to do also is that I'll start distributing the change in t, so this times that here. So this means now here I'll have the change in x is equals to this times that here, it will give me Vi times change in t. Vi times change in t. If we also distribute this to this times that, it will then give me, I'm going to write this as 1 over 2, right? Just to take the 1 here and this and write it as 1 over 2. But notice then that here I'm going to have my A as it is, and what's happening here is that I will have, maybe if I could sort of do this on the side, I'll have the change in t times the change in t. If you look at this, I can take them as exponents to say I keep the base and I add the exponents, because remember this is to the power 1 to the power 1, right? Or you can think of it as if it's x times x, which is x squared, whichever way works best for you. This would then be changed in t squared. Now this is our third equation of motion. And again, this equation becomes true or valid if and only if the acceleration is constant. It does not change, right? Because remember, in this equation, I used the equations that we have already derived under the condition that the acceleration should be constant, right? So these two equations, I combine them, which already we know that the acceleration should be constant on those equations. So this automatically means this equation as well should occur when the acceleration is constant. I'm going to call this equation 5 as far as deriving our equations, but it is the third equation of motion. This formula defines the displacement of an object at any time change in t in terms of the initial velocity and constant